Hello everyone, today we're going to talk about operations with monomials, which, to be fair, we have been introduced also in the last video when we talked about reducing to normal form, but today we will officially cover this topic. So let's start with the easiest one, I would say, although it's not really the easiest one if you think about that, but that will make sense in a moment. So let's start with addition and subtraction. Let's start with some definitions. The algebraic sum of two monomials is still a monomial only if monomials are similar to each other. So recall the meaning of similar monomials. So this means that they have exactly the same literal part if they are reduced to normal form. And then if they are similar, then the result will be a monomial similar to the original ones. However, in this definition, we use the term algebraic sum. And this is something extremely important in algebra, and not only algebra, I would say. So let's define what algebraic sum means. If we want to talk about an operation which could be both an addition and a subtraction, then we want to talk about algebraic addition. And the result of the algebraic addition is algebraic sum. So you will hear the term algebraic sum sometimes also misused, but you will hear this term tons and tons of times. So we'll stick with it, we'll use it because it's extremely important when we talk about algebra and also science in general. So let's do some examples. Addition, a squared plus 3a squared. This is a normal addition, and then we will see how to find out the result. Subtraction could be 5b cubed minus 2b cubed. Okay, here we have plus, minus. This is pretty straightforward. An algebraic addition is 4a squared b plus 6a squared b minus 8a squared b. So it's not important to have both plus and minus in the same expression. 4a squared b plus 6a squared b would have been an algebraic addition anyways. 6a squared b minus 8a squared b would have been an algebraic addition anyways. But here we can see that if we want to express something that is more than a simple addition, more than a mere subtraction, then this is the term we are looking for, algebraic addition. And the result of this is the algebraic sum. Okay. Generally speaking, we talk about algebraic sum. Okay, this is much more used. So when we add similar monomials, their literal part does not change. Okay, I want to remark that we are talking about similar monomials. Okay, because if we sum two monomials which are not similar, then the result will not be a monomial. It will be a polynomial, but we will see this in a following video. However, keep this in mind. Okay. If we have 3 apples and then we buy 2 apples, how many apples do we have at the end? We have 5 apples. Okay? If we have, or maybe a dealership, a car dealership has 4 cars and they sell 1 car, how many cars do they have left? Exactly, 3 cars. If we have 5x and we add 3x, how many x do we have? 8, right? So this is the concept. This is the reasoning we're looking for. So sometimes, especially if you're beginning to deal with literal parts, it might seem a bit difficult to think about 5x plus 3x, but all it really is if I have 5 apples and I buy 3 apples, how many apples do you have left? Okay, so It's just counting, because that x is something, is an object. If you think about this way, it will be extremely easy to do any kind of calculation. So that x means something. If I have 5 of something and add 3 of something, or subtract 3 of something, or multiply 3 of something, or divide by 3 of something, how much something, I don't know how to say that, do I have? Okay, that is the question. If I have 5 cars and I subtract 3 cars, how many cars do I have left? It's the same thing as saying 5x minus 3x. Okay, this is the logic, and it's extremely important. So if you find this hard, repeat this slide multiple times. I know it's not that easy maybe at the beginning, but once you get this, you will never, never, ever forget this. So let's go on. Let's see what are opposite monomials. Opposite monomials are two monomials which are similar but whose coefficients are opposite. That means they have the same number but different sign. Okay, and the algebraic sum of two opposite monomials is 0. Here I have an example. If I have one cucumber, okay, and then I eat one cucumber, how many cucumbers do I have left? Simply 0. I don't have any cucumber left. So if I have x minus x, how many x's do I have at the end? 0, right? X minus x, 0. If I have 3 apples and I eat 3 apples, how many apples do I have left? It's like saying 3x minus 3x, and that is equal to 0. Okay? So what you want to do is do the arithmetical operation with the coefficient and then basically attach the literal part in the end. This works, of course, as I said before, only if they are similar. If I have 3 apples and I subtract 3 lemons, what is the result? Okay, it's simply 3 apples minus 2 lemons, or 3 lemons, whatever I said. Okay, you cannot subtract different things, add different things. So right now we'll just talk about similar monomials. Now let's talk about multiplication, which is not that hard actually. So the product between 2 or more monomials is always a monomial, and the coefficient is the product of the coefficients, okay, of the monomials well taken into consideration, they were multiplying, and the literal part, we just put together the letters and sum the exponents. That's basically what we're going to do. So here's an example. 5y squared times negative 2y. Okay? So let's follow point 1. 5 times negative 2 is of course negative 10. Now let's follow point 2. Just take the letters, put them together. In this case we only have y, so we'll only put y there in the result, and then sum the exponents. So this is because it's a rule of exponentiation, of course. Okay, when we multiply two things that have the same base but different exponent, we are going to sum the exponents. Okay, same base but the sum of the exponents. In this case, 2 plus 1 equals 3. So the final result is negative 10y cubed, simply. Now let's look at an extension basically of multiplication, which is exponentiation. To calculate the power with exponent n of a monomial, we raise to exponent n its coefficient, okay? So the coefficient raised to the nth power, and we multiply by n each of the exponents of its letters. Okay, this is, as I said before, a property of powers. It's the power of a power. So we multiply the powers. So we have the monomial negative 2a cubed bc squared, and we square this monomial. Okay, so the coefficient is negative 2. This is really important. It's not 2, it's negative 2. Okay, And when we want to square a negative number, we need to put the parentheses. Okay? So saying this thing here, negative 2 squared, and saying negative 2 squared is completely different. Okay? Because negative 2 squared is equal to 4, okay? While negative 2 squared is equal to negative 4, okay? This is extremely important because this 2 here only refers to this 2 here. This negative sign is not considered, okay? This is fundamental. Okay, then for the other things, we're just going to do a to the 3 times 2, which is the 2, of course, is the exponent. So we're going to do 3 times 2, 1 times 2, 2 times 2, and this is pretty straightforward, I guess. Now let's talk about division. Division is always that operation which is problematic, okay? In the natural numbers we see that, or in the whole numbers, it's not always possible, it's not an internal operation to that set, number set. This is why we have real numbers. With monomials it's kind of the same thing, because if we don't have multiples then it's hard to deal with this, but we'll see this now. So a monomial is divisible by another monomial when all the letters of the second of the letter, basically, so the divisor, appear in the former, which is called dividend, each with an exponent greater than or equal to that with which it appears in the divisor. In this case, the dividend monomial is said to be a multiple of the divisor monomial. Okay, this is basically what I said, a bit more formal, but let's see what this means with a practical example. Okay, because yeah, the definitions are always good, but at least the way I see it, you get to fully understand the definition when you see it practically applied. So let's see an example and then you will probably understand the definition. Okay, let's just point out that the divisor must not be 0, okay? Usually we do not want to divide by 0 in maths, except certain cases, okay? We will see them in an extremely future video at this point. Okay, if we don't have multiples, as we said in the definition, the result is not a monomial, okay? So we do not like that in this video. So, for example, 6a to the 5th b to the 4th divided by 5a cubed b. So we are going to divide the coefficients similar to what we did with multiplication. In multiplication we multiply the coefficients, here we divide the coefficients, and here, due to the property of exponents, of powers, we're going to subtract the powers. So we do 5 minus 3 and then 4 minus 1, because when we do not have a power, okay, it means that it's 1. We can infer that, okay, it's 1. So this is the result. It's extremely similar to multiplication, basically. Now let's see something new. The greatest common factor and the least common multiple. The greatest common factor of 2 or more monomials is a monomial that has as its coefficient the greatest common factor of the absolute values of the coefficients if they are all integers, and the number 1 if any monomial has no integer coefficient. Okay, we will see this, of course, with an example. And as the literal part, the product of the letters common to all monomials, each taken once and with the minimum exponent. Okay, let's see an example. These are our monomials. We have 3 monomials. So we are basically dividing the monomial in different parts. We are looking at each letter individually. Okay, so in the first monomial, x is x to the 4th and x to the 6th and x to the 3rd. We want to find out the smallest power, so we're going to take x to the third, which is x cubed. Same thing goes for y, and same thing goes for c. Not all monomials have c, okay? So we shouldn't consider this, but actually with monomials we saw in the last video in an exercise that if the power is 0, then we can kind of consider that. So in this case I didn't take it, but you can also see it that way. So c to the 0th power is equal to 1, so that would be the smallest one present between our monomials. Then 3 over 2, 1, and 2 over 5 are definitely not integers, or at least there is at least one which is not an integer, so the leading coefficient will be 1. So the final result is x cubed y. Okay, as I said before, if there is no exponent, we can infer that it is 1. Now, the least common multiple of two or more monomials is a monomial that has as its coefficient the least common multiple of the absolute values of the coefficients if they are all integers, the number 1 if any monomial has no integer coefficient. So this is extremely similar to what we said before, but we are dealing with LCM and not GCF. And then as the literal part, the product of all the letters in at least one of the monomials, each taken once and with the maximum exponents. Okay, so we need to do the product with the maximum exponent. This is the exactly same table, but we are going to do the greatest one. Okay, and even though it is not present, we're going to take the greatest one. Okay, similar to what I said before. If we consider c to be 0, c to the 0th power equal to 1, then we are always going to take something, okay? But anyway, even if it's not present, you can take the largest one. And then we're going to do the LCM of the constants. In this case, they are integers, so the least common multiple is 4, of course. If you don't know how to calculate the LCM and the GCF, just look at arithmetic video, because there are a lot of them which explain how to deal with these operations. But as you can see, it's pretty straightforward. Okay, so when should we use these? We will see them in a future video talking about algebraic fractions, because if we want a common denominator, we will use this. Okay, LCM, totally. It will be fundamental to know how to use this. So if you want a way to remember greatest common factor, least common multiple, so remember that if we want to find a divisor, okay, one of the monomials must be a multiple, okay, as we said before. To do a division and get a monomial, one of them must be multiple. So what we do is get all the things that are in common, not anything more, okay? Because if something is not in common, then the result of a division wouldn't be a monomial. While with the multiple, we do want the smallest multiple, okay? Because if we divide this multiple by every single term, we'll get another monomial, okay? This is the main idea. It's a slightly different thing, okay? I think that for today is enough. This video is almost 20 minutes long. Hope everything's clear. Tell me in the comment section below if you have any doubts. Bye.